Hello everyone, November 12th. I think we did this one yesterday. Alright, as of today, count the number of fair pairs. 0 indexed integer array, 2 integers low and up. Return the number of fair pairs. A fair pair is a pair if I is smaller than j and the sum is in between. So we have a low, we have a high. We want to find all the pairs such that, and it cannot be the same number, such that their sum is in between. So the sum is in between. So 0, 1, 7, 4, 4, 5. I mean, it doesn't really matter, so we can actually sort it. It's just kind of intuition, you know, we want to sort it. It may be helpful. Okay, so now after sort, we want to see from 3 to 6, right? So for 0, I need to say 0 plus something is in this range, right? So which means this should be in the range of 3 and 6. So we can put 3 in here for binary search, right? 3 in here, binary search, the bigger. So 3 in here, if we binary search, will hit this one. And then we'll do 6. Binary search will hit this one. Right, so the number in between is this minus this. 0, 1, 2, 3, 4, 5. So 5 minus 2 would equal to 3. Right, that will be 3. That's for 0. And then you do 1. Maybe we can do 2 pointers, you know. So for the smallest, I go because it's going to be 1 plus something, right? So for 0, it's going to be 3 to 6. So we find first one, and we need to find the first one. Okay, so this is kind of I, this is kind of j. Okay, now move on to 1. So for 1, so 1 plus something is in between this. So that something is going to be 2 to 5. Right, so it'll be 2 to 5. So 1 need to find something that's smaller, that's larger equal to 2. So yeah, if you think about it, the smallest number has this range, which means if it adds those will be, so the whole range will shift left. Right, the whole range will shift left. So basically for here, for I, I'll shift left and to find the first thing that's larger or equal to 2, and then yeah, it doesn't change. And then this one is small equal to 5, so also doesn't change. That's also 4, 4, 5, right? So basically we need to say if the left is still larger than, then we'll shift. But now it doesn't shift, so plus 3. Next we're gonna handle 4. So for 4, we require is 4 minus 3 is minus 1, and 4 minus, no, 3 minus 4 and 6 minus 4. So we'll do this, right? 1 to 2. Now the thing is, once we hit someone, and if this index goes to the left, that means we can now go, right? We can now go. So in this case, I need to go left until the first one that if it's still larger than, right? So I can actually go to 0, right? I actually go to 0. I go to 0 because we just keep going until we find. So as long as it's larger, right? As long as it's larger or equal to, we just keep going, and I'll go to 0. This one, if it's larger than 2, then I keep going. So I is here, j comes here, right? J comes here. Actually, no, j comes oh, ooh. If it's equal, then we don't. So j actually comes here. No, it's larger. So yeah, j comes here. Right, j comes here. So the requirement is j must be larger than this. Both I and j must be larger than the current value that's getting pointed at, because I want to find to my right who I can go with. Right. So in this case, it's bad, and if it is bad, keep going will be bad. So I can just skip here. So that's why it's this. All right, let's try the next one. It's 1, 2, 5, 7, 9, right? And we do 11 to 11. So the first one, we need to find a 10 and 10, right? We need to find a 10 and 10. So I will go. Actually, the first one, okay, binary search for I, right? So binary search for I is already on the outside. And next one, j is also on the outside, so both are on the outside, right? Both are on the outside, so there's nothing, right? Nothing can do. The next one is going to be 9 and 9. So we'll start from I, which is to go in, as long as it's larger, larger or equal to 9. So I comes here, okay? J, as long as it's larger, so j doesn't change. So now we have 1. So 2 and 9, right? We have 1. Now go to 5. 5, what we require is 6 and 6. So as long as it's larger or equal to, so I comes here, okay? And j need to go for something that's larger than 6. So we go here, then we go here. This cannot go, so j is coming here, and then there's nothing, right? Now we go 7. 7 requires 4 and 4, right? 7 requires 4 and 4. Then I goes to 5, right? And j, as long as it's larger, j goes here. So both are here to the left. So yeah, still when j goes to the left, that's it. That's it. Because if j is here, I can use the larger of these two to handle. So yeah, so this is it. 7 has nothing. Yeah, should be larger or equal to 4 and a smaller or equal to 4. And we don't have anything smaller or equal to 4. Okay. So in this case, let's try this. I mean, we definitely can just binary search the entire thing. Every time you do, just binary search. Every time you do, you binary search. I think it will work, but let's challenge ourselves with something, a little bit more not binary search, Well, we still binary search, but just use it once. Okay? We use binary search once, and then for the rest of the time, we don't. So we say arrays.sort nums, okay? And then we say interest equal to 0, and index equal to arrays.binary search nums 0 minus lower. I don't know, minus lower. Well, if you binary search, actually, You know what? That's not binary search. Let's just go I and j. Right? I just go I and j. And then for the first one, we just keep going. Right? We keep going until we find something that's larger, the first thing that's larger equal to this minus lower, right? First thing that's larger and the first thing that's bigger, yeah. So we say for int, no, we didn't do int I, 0, int j is 0. K equals 0, k smaller than nums.length, k plus plus, okay? If nums k is nope, while I smaller than nums.length, okay, if nums I is larger or equal to nums lower minus nums 0, then we'll break I plus plus, right? And then int j equal to 0 while j is smaller than nums.length. If nums j is larger than upper minus nums 0, now we break j plus plus. Right? Because this will find the first thing that's bigger than it, and then the other one is to find the first thing that's larger or equal to it. So when we do this, then we find out, right? We get I and j, and then rest plus equal to j minus I. Okay. Then, okay, it is possible, because I'm already smallest, right? So the impossible case is impossible case. I think I can immediately find out impossible case. So while because we now move I and j to the left. Right now we're gonna have k. So we say while j is larger than k. Right, j must be to the right of k. Then j is larger than k. Then we'll move I, right? Move I to the left. So we shall say while I is larger or equal to 0 and no, while I is larger than 0, because I'll need to check the left, and nums I minus 1, right? If it's larger or equal to lower minus nums k, I minus minus. So we keep going until we find a one that's still larger or equal to, right? Now we stop. And then we do the same thing. While j is larger than k, right? And if j larger than k, and then this. What we need is this should be larger. No, this should be smaller equal to, right? If this is smaller equal, no, if this is larger then we move. If it's larger then we move, then we move. Nope. I think it should be larger than 0, and nums j minus 1. If it's larger than upper minus nums, okay, right, then j minus minus. Right? If it's larger than this, then we can move. If it's larger than, then we can move. If it's larger than, we can move. If it becomes smaller equal to, then we don't move. And the other one is if it's still larger equal to, then we move. Okay. So once we are here, then we can check, right? We say if j is large, if j is smaller equal to k, then we break. Otherwise, rest plus equal to j minus math dot maximum I or k plus 1. Alright, so we've done k plus plus. J this and k smaller than nums dot length. And at the end, we'll return rest. Okay. Okay, we can give it a shot. I am not very confident because this is a little bit fancier solution. Now we can definitely, after sorting the nums, right? After sorting nums, we can solve this problem by using binary search on each value, on each number in nums. This will run O n log n time. However, we can also use a sliding window technique. O n log n plus n log n time, right? Where we keep track of the range of numbers that satisfy fair pairs. When a new number is encountered, it is bigger than the previous, we shift the window to the left, right? And this will end once the right index is touches the index of the current number. So this will run n plus n log n, the sort is plus n time. Okay, let's see if it works. No, it does not. We have a little bit issue. All zeros, output 16, it should be 15. Okay, so what happened here? So in this case, 0 starts, right? I is he. Oh, maybe it should be I should be start with 1. J should start with 1 as well. should not contain the original one. Okay, so we move I and j. Nope. Did we move forward? 52. No, we didn't move forward. Answer is long. We need to do long. Shoot. Okay, so answer is long. But index is okay. Okay, index is okay. Everybody else is, oh yeah, it's 10 to the 9. Wait, no, it's 10 to the 5. Oh, yeah, because you have a lot of pairs. So we need to do long. Okay. Let's take a look. Yeah, I can see how this will cause more issues. Just because of the long, long. Yep, that's it. I mean, it was correct, right? It was correct. Then it's just require a little bit fix to get it right. Amen. If you ask me to do it again, I think I'll still fail on these 2 points. This is a big bug, I didn't notice. And the long is another issue. Binary search, yeah, you can definitely just binary search it. 2 pointers, you still need binary search, but then after that you can do 2 pointers. It looks like it's simpler than my calculate lower bound minus lower bound. Oh, the lower bound of the value. That is true. You are calculating the lower bound. Upper plus 1. Exactly. Lower bound of this and lower bound of lower. And when you do that, wait, how is this 2 pointer? Nums left plus nums right. Oh, wait, hold a second. It's a different way. It's different. It is, consider the sum of these two. If the sum is smaller than the value, then we move upper plus 1. Oh, it's all the pairs whose sum is smaller than that, smaller than upper plus 1, and all the pairs smaller than lower. I see. Very smart. Which means when you're doing it, you have the sum. If the sum is smaller, you add the entire thing. Yes, because everybody in it can handle. Right. Right minus left, and then Right minus left. Are we miscalculating? Oh no, yeah, that's right, because you cannot add yourself. Okay. Right minus left, and then you left plus plus. Yes, left plus plus. If it's larger than right, no, minus minus. Oh, holy crap! This is easy. This is very easy. Yeah, I think I like this one. And I think I'm gonna implement this one. We still have some time. 5 minutes. We can implement this. Yep, let's implement this. Not sure if it's gonna be faster, but it's definitely another idea. Okay, let's try this. We say solution 2. This is from the official solution. We just need to find the total number of pairs whose sum is smaller or equal to upper, or in other words, smaller than upper plus 1, and the total number of pairs whose sum is smaller than lower. The difference between these two counts is our answer. Very brilliant, right? Very, very brilliant idea. Alright, so what we can do is we'll do here private long count lower thresh, right? Int no long rest equal to 0. Int I equal to 0. Int j equal to nums.length minus 1. While while what? I smaller than j. Right, if nums I plus nums j is smaller than threshold, which is good, right? And rest plus equal to j minus I. And then I plus plus. Else, if I plus j is larger or equal to threshold, it's too big, then we need to move j minus minus. Alright, and then at the end we'll return rest. And we'll stop this if I and j meets. Basically just saying, like, it's too big, it's too big, too big, too big, boom, you hit it, and then it's end. It's end, right? So here, first thing to do is, of course, I don't know what happened here. Alright, so first thing is arrays.sort nums, right? And then we can just do return count lower nums. Threshold is going to be upper plus 1 minus count lower nums and lower. Lordy, this is simple. Oh, see doozy. Nice. This might be faster actually. Yep, it is faster. Slightly, but faster nonetheless. Alright, that will be it. I mean, mine is not that bad anyway. I will see you guys tomorrow. Adios.